Hello everyone, and welcome to my presentation about relevance-based comparison of cataract surgery videos using convolutional neural networks. Cataract surgery is the procedure of replacing the eye's natural lens which suffers from transparency degradation by an artificial lens. A binocular microscope is used during the surgery to enable accurately watching the patient's eye, and the output of this microscope is always recorded and stored for some postoperative purposes. Due to storage limitations in hospitals, however, these videos are deleted after a short time, and this great source of information cannot be fully utilized. As you can see in this figure, just a small fraction of spatio-temporal content in these videos is regarded as the relevant content. Accordingly, we have proposed, implemented, and evaluated a novel relevance-based comparison framework that consists of two modules: the relevance detection module that is responsible for detecting the spatio-temporal relevant content in these videos, and the comparison module that is responsible for providing a high comparison ratio while retaining the high quality of the relevant content. We have 5 different scenarios for the relevant content. For example, in the second scenario, all the idle frames are regarded as irrelevant content, and the idle frames are the frames in which no instrument is visible. Also, in action frames, only the regions of the cornea and instruments are regarded as the relevant content. For idle frame recognition, we use the residual networks to classify the input frames as idle or action frames. For ROI segmentation, we use the mask CNN network that can be split into two subproblems: object detection and semantic segmentation. For object detection, a region proposal network is used. The RPN suggests different anchors for each object of interest, and based on the class probabilities of each anchor, the anchor with the highest class probability is selected as the bounding box of the object of interest. Afterwards, a fully convolutional network will provide pixel-wise predictions with the same resolution as the original input of the network using these low-resolution detections. Here you can see the patterns of idle and action frames in 4 representative videos of cataract surgery. For ROI segmentation, we have achieved at least 80% intersection over union for mask segmentation and at least 85% intersection over union for bounding box segmentation. This figure shows the PSNR values for an exemplary segment of a cataract surgery video using different QP differences. In other words, a same quantization parameter is assigned to the region of interest while reducing the output bitrate by assigning a higher quantization parameter to non-region of interest. This figure shows the percentage of bitrate reduction resulting from different scenarios and different QP differences. As it can be perceived, we can gain up to 23% storage space reduction in the first scenario and up to 68% storage space reduction in scenario 5. This figure shows the PSNR of ROI and output size corresponding to an exemplary video compressed in different scenarios. As you can see, we can retain the high quality of the relevant content in different scenarios while reducing the overall size of the compressed video. Here, you can compare the quality of the original video with the video compressed based on scenario 2, scenario 4, and scenario 5. And it shouldn't be left unmentioned that this framework can be generalized to all sorts of surgical videos where the domain knowledge is required. If you have any questions, please don't hesitate to contact us. And thank you very much for your attention.